Hi class, we are now starting chapter 7. We're going to discuss formula mass and percent composition. We're going to spend 2 weeks on chapter 7, but do not wait till the last minute because this is now going to start involving more math. And some of it can get a little complicated if you don't stay on top of it because there's a lot of information to learn, which is why you're given 2 weeks on this chapter instead of 1. This is for my Chem 10 class, spring of 22. So let's get started. The masses of elements and compounds, they play a vital role in chemistry. Chemists use mass to identify unknown compounds and to understand and predict chemical reactions. So if we look back at chapter 3, the periodic table shows the average mass for atoms of each element. When working with compounds, we use these atomic masses to calculate the mass of a single molecule or formula unit. This is called the formula mass. For example, what is the formula mass of water molecules? So we want to know the mass of a water molecule. What does it weigh in a sense? We know that a molecule of water has its H2O. It contains 2 hydrogen atoms and 1 oxygen atom. Using the masses from the periodic table, we can calculate the mass of water as 2 times the average mass of the hydrogen atom plus 1 times the average mass of an oxygen atom. So we end up with 2 times 1.01 U, and U is for the atomic mass, and plus 1 times 16 because there's only 1 oxygen atom. And remember, we use U for the atomic mass. We add these together, and the water is 18.02. So how would we use this? Well, if we think that we have water somewhere else, we can investigate that whatever the substance is. And if we can determine that the mass is 18.02, then out of a process of elimination, then we can pretty much say that we're on track to believe this is water, and then continue on with more tests that we know we can confirm that it would be water. So it's kind of it helps in trying to determine an unknown substance. So when you hear the word formula mass, that's the mass of a single molecule or formula unit. Molecule is, remember when it's nonmetals that share electrons. Formula unit is ions. But honestly, people get really lazy and they start crossing over terms, and they pretty much mean the same thing. So formula weight, molecular mass, molecular weight, and a lot of these terms tend to be used across the board for ionic compounds and covalent compounds. And what the main one is molecular weight. Even though when you're dealing with ions, you're not dealing with molecules, you're dealing with an ionic compound. But it's one of these general terms that gets thrown around, and everybody still understands that you're asking for the mass of a compound. So make sure you understand formula mass, the definition of it, but also when you start seeing things, the words get interchanged a lot more than they should. So that's where I'm bringing up these terms, but they still all mean the same thing. What is the mass of the molecule that you're looking at? Okay, so let's take a look at another example. Here we have potassium carbonate. It's a common water softening agent. What is the formula mass of this compound? So formula mass is the way to ask about ionic compounds. So potassium carbonate has a formula of 2. You have 2 potassiums, and then you have a polyatomic ion of carbonate. So we have to look at all of this. So here we have 2 times the mass of potassium plus 1 times the mass of carbon and 3 times the mass of oxygen. And we add this together, and you can see this is from the periodic table. The mass is 138.21. So this is how we're going to now start looking at compounds and building them up. So you have to, one thing I want to point out, you have to account for each one. So in this case, there's 2. In this case, there's 3. And you have to account for all this. So reading, make sure you understand. Sometimes you're just going to be given the name, and you're going to have to know how to write it out. And if you don't do it right, you'll forget that there's 2 of these, and now your mass is wrong. Okay, so let's take a look at some more examples. Calculate the formula mass of phosphorus tribromide. This is a perfect example where you're given just the name, but you don't, if you don't know what that looks like, your mass is probably going to be wrong if you're not doing it correctly. Particularly for the second one, calcium nitrate, because that's going to be, if you just add nitrate and calcium together, it's going to be wrong. Why? Because I actually now just caught that I didn't put a 2 here. There should be a 2 there. I apologize. Oh, look at, I fixed it right there. So make sure you know how to write these out. And the mass for this is 270.67, and I wrote it out with the masses. The grams per mole, we haven't covered these units yet, and honestly, this is the units that we use. I don't ever really use U, except for as, examples in teaching. But when we're actually doing other things regarding lab and stuff, we tend to use grams per mole, and we're going to start covering that chapter, what those units really mean later on. So just more focus on what I'm presenting. Don't really get caught up in the units right now. So in this case, we have 1 phosphorus and 3 bromides. So you have to make sure you account for that. And that gives you the 270.67. This is a particular one I want to point out, calcium nitrate. Because if you don't remember that calcium has a 2+ and you forget to add 2 nitrates to it, then this number is not going to be correct and you're going to obviously have a wrong answer. So you have to account for everything. So here we have 40. In nitrate, it's made up of nitrogen plus 3 oxygens. So 40 for the calcium. Nitrogen is 1, but we have 3 oxygens we have to account for. Plus we have to times it by 2, but I actually messed this 2 up. The 2 should be right here because this whole thing is there's 2 nitrates, not just the oxygens. So this is an error on my part. So make sure you understand that you have to account for 2 of these. So it's 2 times 14 and 2 times 3 times 16 to account for that because there's 6 oxygens here. So the mass is 164.10 grams per mole. Okay, so now we're going to look at percent composition. Chemists sometimes describe compounds by the percentage by mass of each element in a compound. This is called the percent composition of a compound. We calculate percent composition by dividing the mass of one element in a compound by the total mass of a compound and converting it. What does this mean? Well, what this is that, say, for instance, let's jump back over here. We want to know the percent of calcium that makes up the entire compound. We'll take the mass of calcium and we'll set it up on top of the whole mass of the entire compound. And that's what this means. We take the mass of the one element we're interested in. We set it up over the total mass of everything. And remember, percent is always out of 100. So think of a pie. If we're looking at a pie, we want to know how much if we cut a slice. What is the percent of that slice compared to the whole thing? So it's always out of 100. If it's not out of 100, we're not dealing with percent. And we always take the whole. So the way I try to look at this is we take one part over the whole. And that's how you set this up. So let's take a look at an example here to help get us to understand this. Okay, so this looks like a really busy page, so I'm going to explain what's happening here. So let's look at octane, a component of gasoline. And octane, if you go into organic, the naming is different. So I'll give you a little hint on what it is. So here's the compound right here. It has 8 carbon. So because it has 8, that's oct. So that's where this oct comes from. And the ane means it's a single chain, which means there's no double bonds in it with the carbons attached. If it's octene, there's double bonds, but I digress. So the oct in front is how we name the carbon molecules in organic. So in this case, oct tells you 8 carbons attached to it. So it has a molecular formula of C8H18. What is the percent composition of carbon and hydrogen in octane? So the first things we need to do is determine how many of carbons and how many of hydrogens are in it. So this compound contains 8 carbons, and the mass of the carbon in the molecule is 12.01. And then with hydrogen, we have 18, and the mass for hydrogen is 1.01. So we multiply those, and we end up with the mass of carbon. The total for this is 96.08, and the total mass of hydrogen for this compound is 18.18. So we're going to add these together because remember, we need the total. That's the whole pie. And in this case, it's 114.26. So we account for everything here, we account for everything, and this is the total. So this total mass accounts for the mass of octane. All right, so now we need to know the percent composition of both of them. So the percent composition should equal 100 or close to it, because sometimes we need to round numbers up and down. But it should equal very, very close to 100. So let's take a look at carbon. So if we jump back to the formula, we have mass of one element over the mass of the entire compound, which would be the whole pie. And we're looking at a slice or 2 or how many that we want to deal with. So in this case, we're going to take the percent of carbon, the mass of carbon over the total formula mass, always times 100, and sig figs still count. We are always, from the minute you learn sig figs, all the rules still apply. So in this case, we have 96.08 over 114.26 times 100. This gives us 84.09. So the percent of carbon in this compound is 84.09. Now there's two ways you can do the next one. You can minus this by 100, and that will give you this math. Or while you're still learning it, you should do each step. So in this case, because remember, it's all out of 100. So if you subtract 100 from 100, this number from 100, it's going to give you this. But I would verify that just to make sure that you didn't make mistakes, honestly. Always make the effort, because you'd be surprised how easy it is to make mistakes in chemistry if you haven't already discovered that. So now we take the mass of hydrogen over the total formula times 100. We have 18.18 over 114.26 times 100, and this gives us 15.91. I would just confirm it both ways just to make sure I'm on the right track. And this is now telling me the percent of hydrogen is 15.91, percent of carbon is 84.09. So now we know the percent makeup of this compound. Why does that matter? We'll cover that later. Okay, so let's look at another one here. What is the percent by mass of bromine in this compound? So remember, here's the formula. It's asking for bromine. So we set up the mass of one element over the mass of the compound. So we take bromine, there's 3 of them, gives us a mass of 239.70. So we set that on top. We take the total amount, times it by 100, and the mass of the percent by mass of bromine in this compound is 88.46. Now the term percent by mass means that we're using either atomic mass or we're using grams, which we haven't started learning about yet. That's telling us we're using those units, and it'll usually specify what type of units, whether it's the U or it's the G in grams. So don't worry about that right now. But I just want to, we're going to expand on this because we'll start learning about percent by volume. So the term tells you right here, percent by mass, that this is, we're either using U or we're using the G on this, which is grams. Okay, so let's take a look at another example. What is the formula mass of carbon dioxide? Now this is interesting because carbon dioxide is 2 nonmetals, so they are not ionic, but formula mass can be used across the board, just like people tend to use molecular weight across the board, even though that tends to apply more for nonmetals. So don't get stuck on the term in itself, because they get used interchangeably a lot. But the correct term would be formula mass for ionic, and your book is using it also for this. But I just wanted to point that out. Okay, so what is the formula mass? It took away the top. Okay, so let's look at it. What is the formula mass of carbon dioxide? That means that you have 1 carbon and you have 2 oxygens. So the answer to this is 44.01. What is the percent of carbon in carbon dioxide? So in this case, we know that we have CO2 is what we're dealing with. So we have 1 carbon, but we have 2 oxygens. So with the carbon, we have 12.01. The total mass of this compound is 44.01 times 100. And the percent of carbon in this compound is 27.29%. Okay, what is the formula mass of iron 3 chloride? I'm not going to spell this one out for you on purpose, because this is where you guys really have to know how to write compounds out, but I am going to give you the answer. And if anybody has problems, you can always reach out and we can go over any of this. Okay, so why does this matter? This matters because we can identify a compound with the known knowledge that we have about compounds. So if we believe that we're dealing with carbon dioxide, if we can determine the mass and the percent, then we should know that carbon should be about 27.29% of that compound. And if it comes up at that, then again, that's a process of elimination that we're on the right step to identifying that it's probably carbon dioxide. So that's why these masses and percent compositions are so important. But there's also other problems. So chemists often have opposite problems. They encounter a new compound, perhaps something like a natural product, with exciting medicinal properties, and must determine its structure and composition. So this is another way to break it down. And once we get the formula mass, percent composition, we can try to figure out what the compound looks like. So in this picture, this stream of scientists are from the University of Alabama, Birmingham. They collect and study sponges from the waters around Antarctica. And some compounds discovered in these sponges block the growth of cancer cells. So chemists use the formula mass and percent composition to help determine the structure of these compounds. Both formula mass and percent composition are very important to identifying unknown compounds. All right, so now we're going to look at mass spectrometry. I always screw this up. I don't know why. Mass spectrometry. I know how to use this instrument. I've used it for years. For some reason, though, I have a hard time. Mass spectrometry. When I start thinking about it is when I mess it up, but when I'm not thinking about it, I can say it very clearly. Chemists measure the masses of compounds using a technique called mass spectrometry. It's also known as MS. It's just abbreviated MS. A mass spectrometer contains three vital components. It's an ionizing chamber, an electric field, and a detector. The ionizing chamber converts neutral molecules into ions, often by removing an electron. So it knocks an electron out of it. So you can see here where the M, this is a neutral compound, and it knocks an electron out and it leaves it in ionic form. These ions are then accelerated into an electric field, which causes the pathway of the charged particles to curve, depending on, if it's positive or negative. Lighter particles curve more sharply than heavier particles. After exiting the electric field, the particles strike the detector. The spectrometer calculates the mass of the compound based on the size of the electric field and the charge of the particle, and the precise point at which the particle hits the detector. So there's different types of mass spectrometers. There's different types, but this is the general idea of what it is. And I've used it a lot when I was trying to determine what molecules I had, and when I was synthesizing compounds, if I actually produced what I was trying to produce. I would send it off and have it, and I would get back everything with these little lines, and it would tell me exactly if it matched up with what I was expecting. Which looks like this. Mass spectrometry is routinely used in chemical analysis. For example, forensic chemists use mass spectrometry to monitor for hazardous or illegal substances. This figure shows the mass spectrum of a sample taken from a surface of a dollar bill. Cocaine has a formula mass of 304.2. The signal at this mass indicates the presence of cocaine on the surface of the bill. So this is where this is a nice clean spectrum. Sometimes they're not this easy to understand, and the relative intensity just tells you how much of it, but then you'll see it broken down, because what you'll see is the other compounds I'm not going to confuse you guys. Anyways, this is an example of something that I would get back after I had my compound analyzed. This one's very clean compared to what mine would look like. Okay, so elemental analysis. Chemists measure percent composition using a technique called elemental analysis. This technique uses combustion reactions to convert compounds into simpler products, carbon dioxide and water, for example. The mass of each product indicates the percentage of each element in a sample. The sample is placed in the combustion chamber, and using a combination of elemental analysis and mass spectrometry allows chemists to determine both the percent composition and molecular formula of an unknown compound. And this is how they do a process of elimination, because they already know what some compounds look like. They can compare them, and if they think it's this, then they can go on with another technique to confirm that that's what